Singapore, and in my department of civil and environmental engineering, my work is mainly on digitalization. So I'm only 1/3 of Prof Z. Only 1/3. So I'm just going to quickly introduce myself. So I'm a senior lecturer in the department. I got my bachelor's and my PhD from NUS. I was very fortunate. I had a 2.5-year stint at Carnegie Mellon University as a postdoctoral fellow under Prof. Burcu Akija. And I have been out in the industry, the built environment industry, firstly as a project management consultant, and I spent a couple of years as a BIM consultant before coming back to academia. So in NUS, the things that I teach, which are very closely related to my research, is on computer-aided civil engineering, BIM and virtual design and construction. I also teach a little bit about design for manufacturing and assembly, as well as anything related to advanced construction and advanced construction technology. So in my research group, we try to cover the entire life cycle of a building. So we look at things like intelligent compliant design, which I think is something that's very relatable to this group. I also have my students working on digital construction and planning, virtual design and construction. Recently, we have been very fortunate. We have a couple of projects involving construction automation and robotics. So we have been advancing in that field as well. And something which I did with my postdoctoral supervisor on data-driven building asset management. So we try to cover the entire spectrum of research in the built environment. So we have been, again, like I said, we have been very fortunate. We have had a very good few years getting projects from the industry as well as from the government. So we work very closely with the industry. Quite a number of our projects are sponsored by them. We also have a lot of working relationship with the government agencies. So I think some of the interesting projects that we have is on, the first one is on the drone-based facade inspection system, which I'll talk a little bit more later. We also have projects related to earthwork volume estimation using point clouds, photogrammetry, and BIM. And one that we are currently working on now, which is on monitoring of ground settlement using point clouds. Our recently completed project is on the integrated robotic BIM inspection system, which I will show a little video that we have on that. We also have one where we work with one of our industry partners to create an autonomous robotic excavator. And of course, the last one, which I think is very relatable to this group, is on the BIM compliance and system structures. So in terms of our philosophy, as a research group, we have this thing that we call the 3P framework in our research lab. So it encompasses 3 things. One, process related to information, building information modeling. The other is on product, where we look into automation and robotics as a prime mover, facilitator of the product. And of course, the last one that I think is the most important that I'm trying to get my students on board with is on people. How do we interact with the built environment? So my research group's core themes, right, are focused on these 3 Ps. So just to show some quick examples of how we have used the 3 Ps. So for the first one, that we have developed something we call the crane information models. So the idea is this: if we have building information models of buildings, why do we have of major equipment? So one of the things that we have developed is crane information models. And what's good about these crane information models is that we use this to check on safety compliance, whether when we are presented with a lifting plan of cranes, whether these cranes, whether they fulfill, right, the requirements of the ministry. Not only that, we have actually been able to use this to calculate the reach, and from there we have also been able to use optimization techniques. So harmony search was actually one of the things that we played around with in trying to optimize where we can place the cranes, right, using the crane information models, because that would allow us to see what we can pick up and where we can place the different elements. So that was nice. We worked with a contractor on this, and well, we showed them that we could potentially save them about 100,000 Singapore dollars, and they were quite happy at the end of the project. Now, another one on process, again related to BIM. So one of the things which I'm interested in actually is where BIM is concerned, the major problem with BIM is actually the quality of the information that goes into your models. As much as in academia and in an ideal situation, we tell people that your 2D drawings are actually snapshots of your 3-dimensional BIM. The reality is no. Why? For various reasons, the industry is still developing design documentation in 2D. And then they work the other way around. So from 2D, they will come up with the 3D in BIM. And when they do that, typically what will happen is a lot of errors, right? Human errors will come in and create problems with the model. So we have developed a framework where we use computer vision to compare, right, between the 2D design information and the 3D models. And from there, we try to pick up where are the errors, and from the errors, we try to identify this to the modelers so that they can make that change in their modeling system. Something that we have also developed along the lines of quality assessment and quality control of structural BIMs. So this was working with one of our major consultants in Singapore called Sembcorp. We created what we call as an IQA framework, an information quality assessment framework. Basically, what this assessment framework allows us to do is we can look at the model, and from there we can actually quantify the amount of correct and complete data that we have in the model. And from here, we can actually help to police the kind of information that goes into the model. So we can now assess, right, is this a good model, is that a bad model, based on the requirements, in this case, of a structural engineer, whether they need that kind of information. And so we actually created a little plugin that goes into Revit that will allow them to do, right, as close to near real-time monitoring of the information that goes in. A small, interesting side project that we came up with, again working with Sembcorp, was on the conversion of architectural BIMs to compliant structural volumetric modules. So I think some background to this, Singapore, we have been pushing this idea of volumetric construction. We have our own local term for it that we call PPVC. The problem with this is that the architects, when they do the design, they do not have any concept of how the structural modules are supposed to be created. So we created a plugin to help that process. And so what it does is that the architects, right, they will input their architectural models. Our plugins will go in, our software will go in, assess the model, extract the necessary information, and we will actually convert the model into a structural model. So we can actually take this and throw it into, I know Korean Midas is a very big company here, so we can throw it into Midas, we can throw it into ETABS, and it will do the analysis for us. So we hope that by doing this, we can shortcut that process and reduce the errors from the architects to the consultants. So this is something that I just added today. After Prof. Z sent me his slides from tomorrow, I was like, hey, this is something that I thought would be quite interesting. Now, when we talk about BIM and using BIM for compliance, the challenge is normally in how we code that information into whatever it is. So I believe your group. Sorry, I forgot. So you were saying just now that you had a Python rules, right? A rule concept, and you will find that when you try to do this, right, there's actually a very big discrepancy between the person who knows the actual code and the person who's actually implementing the code. So this is actually what's happening in Singapore, is that the person who knows the code has no idea how to do programming. The person who's implementing the code, who's programming the code, has no idea what that domain knowledge is. So this, we introduced this concept of a conceptual graph. Well, conceptual graph was not from me. We borrowed this concept from somewhere else. And we use this to help to bridge between the code implementers and the domain experts. So by both of them understanding this, so it becomes a common language that they can use, so that they can transfer that information from the domain experts to the code implementers. So I think it's very similar. I believe I saw Prof Z's his notes. I was like, hey, yeah, this is actually something that we've been working on as well, because I believe that there's some flow charts that's being generated by the domain experts. So this conceptual graph works very much similar to the kind of concept as a neutral kind of language that both parties know, so that both can interpret and reduce the loss of information. So we did a study on this, and in this study, by introducing this conceptual graph, we also implemented a way of measuring the quality of the information that goes into the conceptual graph. You can have good conceptual graphs, you can have bad conceptual graphs. How do we define a good conceptual graph? So that's so our work went in to define this, and we then use this in a test scenario to see whether or not we could improve the quality of the information that gets input into the rules. So I thought that was something that nicely aligned with some of the things that your group is doing. So this is the part that we are working very closely with the government agency in Singapore. So we are working with them on using BIM to do structural compliance, code checking of structural elements. So just to give you an overview of how this whole framework works. So in Singapore, when we do structural design, typically the structural designs come from the architects. Right? Before we do the actual structural design, the architect will pass us their models. And from there, we will develop the structural beams, right? Ideally. And from the structural beam, we will then develop the analysis models that we are going to put into the structural and design, analysis and design software. The problem is that what BCA wants, or what the Singapore government wants to do, is they want to take these few models and they want to check, have you done the right modeling? So if you say you have a beam, column and beam in one model, do you have that same column and beam in another model? If you have put information here, do you also have that information in another place? So this is very different, a little bit different from the code compliance systems that you probably have been researching on. So in most code compliance systems today, code compliant is very prescriptive. So that means that the code says, all right, clause 13.1.1, you have an air well must be 5 meters away from something. So that's the kind of code compliance that goes in. And typically this is very usual for architectural codes. Now, structural codes, while we do have some of these, normally the code compliance has already been dealt with by the analysis and design software, right? So if you run your code, right, if you run your models in Midas, Midas is not going to give you an answer that violates the code, right? It can't be, right? It can't be. So structural engineering, when you talk about code compliance for structural engineering, it's a little bit different. So what we're actually doing here is more on, well, one, can we check the models? If you have input certain assumptions into one model, have these assumptions been also input into your analysis and design, and vice versa? And from there, then what is more important that we wanted to achieve with our structural beam compliance system was to see if we could identify good design. So what do we mean by good design? So that's where we went to the industry and we started talking to the experienced engineers to find out what were the engineering rules of thumb. That means at the back of the mind, right, if you have talked to good civil engineers or good structural engineers, they can look at the column, they can look at the reinforcement, and they tell you there's too much reinforcement. They don't even need to do any calculations, right? So we wanted to try and mimic that kind of engineering sense, and we encoded these as rules that we could put into this system. So that's the idea that we wanted to do with this particular project. Of course, there are a lot of small little details that goes in. There are a lot of small little details. So for one, we to do this, we had to align ourselves with the national agenda. So the national agenda is pushing for something that we call CORNET-X. In fact, we are one of the what we call as the solvers, right? One of the model checkers that will be used, right, in CORNET-X in the coming phases. And the other that we did was that we needed to interface with this thing that we call the IFC SG, right? So I'll talk a little bit about IFC-SG tomorrow, right? But I'll just give you a flavor. IFC-SG is an extension of the IFC schema that has been extended to include information that is specific to Singapore. Right? So we have input this thing as the IFC-SG. One of the features that we have actually in this system that we have. So if you look at the picture, we have on the left the structural BIM. On the right, we have the 3D analysis and design model. So two different sources. We also realized very quickly that when we talk to the engineers, there will be instances where the engineers do not submit the information in BIM. Right? So that means we have to take information from somewhere else. So that's where we have created a separate process that allows us to take in 2D analysis and design information, typically in a CSV or an Excel file, and from there we can repopulate into the same kind of schema, and then we can do a comparison and do the checking from both sides. Yeah. So the secret sauce to that, to achieving what we wanted to achieve, right? One of them is actually this thing that we call the cross model information. Let's see, we call it the XMI. So this was developed by my research group. It's a neutral open data schema. So the website is already there. There's a preliminary version 1 that is on there now, where we detail out the different classes. So there are 25 different class entities covering things from structural nodes to structural members, right? Even to structural point connections and so on and so forth. The last I did a count, that was over a year ago. We were looking at over 350 structural properties, right, encompassing all these different 25 classes that is being used in different combinations by the classes. Now this is very much a work in progress. So at this point in time, we have the schema covers the major building elements and materials. So in Singapore, unfortunately, that does not cover timber. So we only cover concrete as well as steel. We cover the major building elements. One of the major building elements that we have not dealt with yet, and hopefully, so I think some of you were talking about joints and right. So I think that there's a lot of room to explore, right? And that's on the connections, right? So especially in Singapore, because a lot of our buildings is built with precast. So the precast connections are actually very vital thing. And that's something that we're going to be exploring in the next phase of our project. How we're going to be incorporating. How do we capture the connection information? So connections are a bit tricky because they tend to be isolated from the rest of the model, and the ways that you can detail the connections are actually quite varied. So we are trying to find a way that we can detail this in a more standard manner. Of course, the XMI itself, the 25 classes covers both the analysis and the design aspects of structural engineering. Okay, so that's for process. So I just quickly run through the product. Yeah. So this is a project that we did with our collaborators, and we partnered with again with our government agencies to address this problem. So the background to this problem is Singapore. You may think that Singapore is a very modern city. It is. Singapore is actually is slightly past 50 years old, and in this 50 years, we have instances of our concrete facade elements actually falling off. So we tried to answer that national problem by creating this thing that we call as the building facade inspection system. So this building facade inspection system uses UAV drones. Works. Yeah. So in this UAV drones project, we do a lot of stuff. We do data collection using drones, and after we have done the data collection, we actually get a lot of images from the data collection. The images also have infrared images as well. From here, we actually do a 3D reconstruction. One of the interesting things that we do with the reconstruction is that we actually leverage Google Maps, right, and use the geometries of Google Maps to augment our reconstructed models from the images. So once we have that, then we also look into the defect detection. This is a very old defect detection using bounding boxes. Today we've actually gone further into using segmentation to segment those. And this is an old prototype which actually we have much improved now, but it shows the main functions and features of our prototype. So we are able to annotate, we are able to capture, place comments, and the reason why we're doing this is because we want to shortcut the process for the inspectors. So the inspectors will use this app, and after they've used this app, they can then generate a report. So typically something that took about 2 weeks, using this app, it takes about 3 days, right, including the data collection process. Yep, so we have also done some work on infrared. So the reason why we're using the infrared, what we're hoping to do is actually to try and see if we can detect delamination, right? Defects that can't be visible, that are not visible. We're trying to see whether we can pick these up using infrared as a telltale early warning system. Okay, so the other big project that we have in our research group is this thing that we call the Integrated Robotic Beam Inspection System. So what we are again trying to do with this system is the key issue that we're trying to do is we find that it takes a long time for the building developers to inspect the buildings. Again, this goes back to compliance. We have many rules, many different things that we need to check in Singapore. These checks could come from the building developers themselves, the building owners themselves, and actually a big part of them also comes from the different government agencies. So to shortcut that process, what we proposed was to use an autonomous vehicle like Boston Dynamics Spot. So we bought one. We worked together with Trimble, and we used a high-powered terrestrial laser scanner, right? In this case the X7, mounted onto the Boston Dynamics Spot, and we went around collecting that information. And the information that we're collecting primarily is in LiDAR point clouds. So we then created, from these LiDAR point clouds, we then created algorithms to try and help us to check and measure, right, the differences, right, between what was originally planned by the building developer and what was actually constructed by the contractor at the end of the day. Yeah. So this was one of the marketing videos that my guys did. I think the project was quite a success. We have started we're thinking about starting up a company to see if we can provide this service to the industry. Yeah, so some of the features, it's robotics agnostic, it's cloud powered. There are inspection algorithms that's inside, and it also interfaces with BIM. Okay, so this is the architecture. Let me. Oops. Oh no. Okay, I'm not sure how to control this. I wanted to fast forward, but okay. Anyway, so we have created a cloud-based application that allows us to collect this information. And what's useful about this is that we interface with BIM. So by interfacing with BIM, it allows us to shortcut one step of the process, which is on segmentation. And from there, we are able to directly annotate the defects and pair this with the elements in BIM. So this actually creates a running archive of defects that we have found in the building. Yeah, so this was one of the projects that we did, and this is the prototype that we have. So again, very similar to the drone project, at the end of the day, the building inspectors will be able to use this app and shortcut, right, their report generation process by using the app for reporting. Okay, so the last one that we have is on people. So again, my group very interested in the use of virtual reality and augmented reality. And one of the key things that we wanted to discover was how effective is augmented reality and virtual reality in construction inspections. We have heard a lot of, when we go out and we converse with the industry, we hear a lot of people telling us, oh, augmented reality, virtual reality is very good for construction inspections. So we wanted to test that. So what you see on this is we created a game, right, that simulated the use of augmented reality and virtual reality in a construction inspection process. And we got people from the industry to come down and try and see if they could identify the defects from this particular game. So the outcome of the game actually showed that it's not always true that by using augmented reality, that would actually allow you to pick up construction defects on site. Right? It's not always true. There are a lot of other things that comes in that affects, right, whether or not a defect is actually being picked up by the inspector. So this is something that we are publishing a paper now on to show that it's augmented reality, virtual reality has its benefits, but for construction inspection, there's a lot more that comes into play, and it's not just the use of the technology that would enable construction inspections. Yeah, we played this with some of the students. They loved it so much because they purposely failed, couldn't find the defects because they wanted to see the retaining wall collapse, and they were very excited by the collapsing retaining wall. So last one that we have. So this is again this is one of the latest work from my PhD student, and that is we wanted to create a method to track people in the building. Right. So if you may have seen some of these where they use cameras, they use infrared, right, to try and see, try and track people in the building. But once you use cameras, then this raises the issue of privacy. So we wanted to use a distributed acoustic system, a DAS, which is an optic fiber-based vibration tracking mechanism. And by using this, we could actually create a privacy-preserving, large-scale occupant tracking device. So we can actually lay this out over many different various floors in the building. And right, we can actually pick up and see how people move from one room to another, whether they walk diagonally across the corridor, and so on and so forth. So this was very useful. So one of the innovations that we did was my student actually created an algorithm, a machine learning algorithm, to try and identify the movement and the footsteps of people using this particular device. So quite successful. We're quite happy with the results, and we are looking to work more on this device. Yeah, so that gives an overview of all the different work that we've been doing in my research group. So let's talk a little bit more about Oh, it's there. Okay, I thought it was duplicated. Okay, so I just quickly run through. Okay, so just to give some background about Singapore, right? Just to quickly skim through because you hear more in depth tomorrow. So Singapore, we have actually introduced something that we call as the CORNET-X system. So the CORNET-X system has been in development for very, very long in Singapore. So the CORNET-X is the latest iteration of this particular system. And one of the things that we want to do with this system is that we want to be able to use this to check the compliance of our building submissions, right, the regulatory submissions. So there are 5 components to this CORNET-X system. So the first component is what we call as the pre-submission check. So pre-submission check means that the inspectors, sorry, not the inspectors, the engineers and architects, before they submit this to the government, they can actually use the system and check through first, right? So basically the system says, okay, you're good, right? They can proceed on to the next step and submit this. So that's the first. The second that has already been developed is something that we call as the CORNET-X portal. So this is a secure system that has been developed by one of our government agencies. that serves as a front-end portal to the whole ConnectX system. So other than this, we also have the automated model checker, which my previous the research project I introduced earlier is one of the many automated model checkers that is going to be developed. So the others will include things like your fire codes, your architectural codes, building accessibility, and so on and so forth. So all these things will come in under the automated model checker. We also have a collaboration platform. So this is the first version of this collaboration platform has already been developed in Singapore. And in this collaboration platform, it's to allow the different agencies to come together and give their comments, right? Because why? The issue with the current CONNET system is that the agencies have no visibility into the comments of the other agencies. So when the design comes to the agency will check, right? And he will propose certain changes, or he'll ask the engineers or architects to make certain changes, but he has no concept, or he has no idea of what the other agencies are going to give. So there have been cases where after after one agency has given his comments, the engineer changes and finds that this conflicts with another agency's requirements. So we have multiple agency requirements that are conflicting. And when this happens, in Singapore, we have to wait for, I think once every month, there is a big, all the agencies will come together and there'll be a big meeting where they will flesh out all these problem projects, and they will discuss and try to see if they can solve it. So it's a very long drawn process, because you imagine, it takes a few months to be able to clear the design for problematic projects. So the collaborative platform allows these problematic projects to come together, and all the agencies to come together and solve them on the spot, because now they will know, this particular comment by this agency A doesn't work for agency B, and agency B can now say, hey, this doesn't work. So that's the collaboration platform. And the last one, of course, is on a centralized data hub. So one of the things that we are hoping to do with ConnectX is that we have, once we start to receive all these information, we are going to put all these information into a central data hub that's going to be stored by the Singapore government. Okay. Yeah, so this is the first version of the collaboration platform. So in this collaboration platform, what's nice is that the different agencies, they can actually customize their views, so they can extract specific agency requirements from these views. They can then do a concurrent review and virtual collaboration like what I described earlier. And once they have done that, they can then issue a coordinated response to the industry after they have finished their collaboration platform. It's okay. I tell you what. Yeah, I'll use my own sales slides. Yeah, I think that will be better.
Do you present the same tomorrow?
No, I think they're missing slides in here, so I'm using my own. Yeah, I'll be using my own instead.
You're also doing a lot of research topics. 3P. Although I have 3 different research groups, 1, 2, 3, but I do not have 3 layers. But you have 3 layers. 3P.
Actually, a lot of times the research is actually determined by the students. So I mean, I just give them, okay, these are broad directions, and then they are the ones who come and tell me, okay, I'm going to do this. Okay. So,
how many group members do you have?
well, now my team is small. I think at my largest, which was last year, before my projects ended, I had about 12 researchers.
12 researchers.
12 researchers and students.
I see. So big group. So bigger than mine.
Now it's small because my projects have ended, and the good thing is my students have graduated. So I'm looking for new students now. Okay. So they said they're missing. Okay, but anyway, it doesn't matter. I'll just quickly run through this. So this is ConnectX platform, and these are some of the changes that we're going to be making with ConnectX, right? Which is to shortcut some of the processes. Okay, so one of the key enablers for ConnectX, right, which is on our Singapore BIM, is the introduction of this thing called the IFC-SG. So I mentioned earlier, the IFC-SG IFC itself is a common, it's a very well-known building data standard, and what Singapore government has done is that we have started to extend, right, on the IFC information. Why? Because not all information that is found in the codes can be, right, is represented in IFC, right? So that's what we have done to enhance that. Okay, so one of the things that we have in terms of our policy of IFC-SG is that in creating the IFC-SG, we have based this on a specific version of IFC that we call the IFC4, and specifically on the use of the reference view, which is the model view definition. And so we are using this, and the reason why we're using this IFC4 reference view is because IFC is a big data format. There's a lot of information that's inside. Unfortunately, actual implementation of IFC is limited. So if you use Tekla structures, if you use Revit, and you look at the exporters that come out, that come with these, normally these exporters are not able to export the full IFC. The full IFC is just too big, too many things inside. It's very difficult to be able to get that. So, the common, right, the common subset of this IFC information that is supported by all the major software is actually IFC4 reference view. This may change in the future. We are looking, Building Smart, which is handling or which is managing the IFC4 reference view, IFC standard. They are looking to get, right, more of the software vendors on board, particularly for the structural analysis part, particularly for the architectural coordination and so on and so forth. So there's actually a lot of changes that's up and coming. But for now, right, for the IFC-SG, we are basing this primarily on the IFC4 reference view. Now, even in the IFC4 reference view, what's the mechanism in which we have started to extend the information? We have veered away from creating our own IFC entities, right? That means we try not to come up with things like IFC ramp or okay, there is an IFC ramp, IFC toilet maybe, right? So new information or new classes of building products is something that we are trying not to get into. So instead, what we have done is that we have made use, right, of IFC's inbuilt user-defined attributes, right, and try and extend the user-defined attributes instead of creating our own. So the IFC4 extension, right, works that way, right. And the reason why we're doing that again, right, is because if we start to create our own elements, IFC elements, then the problem is that nobody else in the world is going to export these elements for us, right? So that's why we have veered away from doing that. So IFC-SG works that way. Limitations, well, I wouldn't say it's limitations, but some of the things that we have to do, right, in preparing these models for submission, we are hampered by size, Okay, so IFC is a huge data format, right? Don't underestimate the IFC file. If you open an IFC file, you see text inside, and so you'll be very happy. It's nothing but text. But text actually takes up a lot of space. So a good sized building, right, would easily come to terabytes of data, depending on how you size the building. So we have actually put in an artificial cap telling all users that you are not to exceed 800 megabytes in size for IFC file submissions. So if you do have, right, because some of the projects are fairly large and complex, we actually advocate that they do a federation of the model, which means that they cut the model into small pieces for submission. And one of the things that we are asking the architects and the engineers to do is to make sure that the models that they are preparing have to be georeferenced. This is actually because some of the codes that we are doing, for example, from the urban renewable authority in Singapore, URA, they are looking at codes that is not just for one building, they are looking at codes that extends beyond, so for a whole group, right, or whole estate of buildings. So because of this, we have also asked the engineers and architects to georeference their models according to the Singapore SVY21 coordinate system. Okay, so there's a lot of, so to allow them to check, BCA has also implemented this thing that we call the IFC-SG validator. So the architects and engineers can actually submit, right, onto a website, and this website will actually check through the model and make sure that all the information that's been entered complies, right, with the IFC-SG data schema. Okay, so you address things like if you have spelled things wrongly, if you have missing elements in the IFC-SG, or you use a wrong property set. These are the common errors that this IFC-SG validator will churn up. In terms of engagement with industry, right? So this is from our learning points based on the 2 years of engaging the industry for ConnectX. IFC-SG is very difficult to implement. Okay, I'm not going to hide the challenge. The challenge is it's very difficult to implement. It takes a fundamental change for the industry because prior to this, they have never heard of IFC. Very few of them have heard of IFC. And suddenly, we are asking them to submit this IFC-SG. So this is a big fundamental change. What we are doing, right? What the government is doing together with the universities is now we're trying to organize sessions, educate the engineers and the architects, right, as to what the IFC-SG is and how do they deal with some of the common problems with IFC-SG. The other complaint that we get from the industry is that, right, it takes a lot longer to model now, right, because of implementation of the IFC-SG. We have tried to automate a lot of the processes that goes into it, but there will still be, right, the added information that will need to be put into the model. So there is a lot of resistance, or there is some resistance from the industry about these longer modeling times. But we are trying to convince them that it is worth it because even though you get longer modeling times, your regulation time gets reduced, right? So instead of waiting 2 months for, right, the submission to be approved, right, we can now give it to you in 20 days. So that's the promise that we are trying to make as a trade-off, right, to these longer modeling guidelines. There's a lot more interdisciplinary modeling, right? So consultants and the contractors, we have to get together earlier in the design process. Okay, and the last one, I think the most important thing is on a consistent modeling standards and guidelines for the industry. We have always been advocating, especially for BIM, consistent modeling guidelines, with IFC-SG coming into the picture even more so. That's why you'll notice that the way that the ConnectX has been set up, checking of models, right, the quality assurance of the models is now a very big thing in the ConnectX. Yeah. So come to my part, which is on the automated model checker for the structural elements. So these were my researchers. Some of them, in fact, most of them have left. So that's a good thing about. I tell prospective students that's a good thing about joining my research group. After they join my research group, the government agencies will take them and pay them good salaries. So. So we had a lot of help from BCA, which is the Building Construction Authority, which is the government agency involved, right? Yeah, so I just run through some of this. Okay, so in terms of our in terms of our modeling workflow, one of our design concepts, design principles when we were developing our project is we try not to change the existing workflows of the engineers, right? Because if you change the workflows of the engineers are going to complain, and they will not, right? They will not adopt the system that we have created. So we try not to touch the workflows. So we have actually identified that there are two common workflows in the industry. One, which is the alternative one, that is the ideal alternative, which means that architect gives us the architectural BIM. From the architectural BIM, right, the engineers will then develop the structural BIM. After the structural BIM, they will then put this into the structural analysis and design to create, right, their analysis and design models. Okay, and once they've done that, we will round trip the information from analysis and design. We will update the structural BIM. Structural BIM will coordinate with the Archi, and that gives us our coordinated final model. Now that is the ideal case, right? But the actual case that most of the companies, most of the engineers are actually doing is that they find that there is not enough time because of our contracting system in Singapore. Engineers actually do not have enough time. So what they do is they shortcut the process. So instead of developing the structural BIM, they go and jump straight into developing the analysis and design from the architectural models. Okay, so there's good, there's bad. The good point is it's shorter. The bad is if you make a mistake, you need to redo your information again. Okay, so those are the two. Those are the two ways that we have going about. Now, having said that, we are not in the business of trying to change how they think about their processes. So we are going to try and see whether we can adapt and accommodate both workflows. We were rather fortunate. We talked to the different software vendors. So there were two groups of software vendors that we talked to. One was the BIM software vendors, and the other were the analysis and design tools. So we managed to get on board this number of 8 of these different softwares. We actually asked Midas, but Midas said that at that point 2 years ago, Midas told us that they didn't have an API at that time, so they couldn't participate. But now we're hoping that maybe I should give Midas a call again.
They're working on their own.
Oh, they're working on their own. Okay, that's good. So the different participating software: Autodesk Revit, Tekla Structures. We also have ETABS SAP 2000 SAFE, which is from CSI, and we have Tekla Structural Designer (TSD), STAT Pro, and Tekla TADS, which is a element modeling software, 2D element modeling software. So we have created plugins for all these different, which means that they are now able to export the necessary information in the right format that we want, so that we can now do the model checking. Okay, so I mentioned this earlier in the previous set of slides. Yeah, so what we have developed as part of this thing, so the first one that we developed was the XMI schema. How do we frame the information so that we can now read and write without confusion? The other that we are now doing, right, or that we have, which is a forthcoming paper, is how do we match the elements. So if you have elements in one model, I have elements in another model, right? How do we know that these two elements are actually referring to the same thing? Okay, don't forget this is different because one is from the analysis and design model, another is from your structural BIM. Okay, so of course, right, as an engineer, of course, if you look at this, you can manually, right, you can say that they're the same. But from a computer perspective, right, identifying this will have a lot of issues. Okay, so we have created ways in which we can now identify the elements and say which one matches which one. And as part of that, what we have done is that we have also created 30 checks and 60 rules. So like I mentioned earlier, the rules that we put in place are engineering rule of thumbs, right? They are not exactly the kind of code clauses that you will find in the engineering Euro code or whatever. So we have created 60 of these, and more importantly, we have actually created 30 checks that would check the information that's being fed into the system to make sure that, right, the model is verified. Now, at the end of the day, what is presented to the user is three things. One, it will trigger a pass, which means that everything is okay, we continue to submit. The second is it will trigger a warning. So a warning actually just means that maybe something is not quite right, or it requires the engineer to put in additional information in the form of supplementary files or something like that. And it's not, we are not going to reject the submission straight away. And the third is an outright fail, right? Which means that there's something fundamentally wrong, right, with the submission, right? And then we'll flag this as a fail, and we'll tell the user. So just an example of some of the checks. So we do. So one of the checks that we do is on checking the total area of the beam longitudinal reinforcement required. Right, it's less than what is provided. So this is actually looking at two different sources. So your analysis and design, at the end of the day, this will tell you how much you need in terms of your longitudinal beam reinforcement. When they input this information into the structural beam, this is actually what is being designed, right? Or this is what is being provided. So there's a difference between these two. So what you need to check is that one has to be greater than the other. So what you provide has to exceed, right, what is required by the project. The other is so this is an example of a rule. So in this rule, we actually have we ask the question: are the RC beams span depth ratio within the expected ranges or norms? Okay, so again, this is the engineering back of envelope calculation thing. So again, right, mimicking an engineer's thinking. So he will look at what's the span, he'll look at what's the depth, he does a quick calculation, and we provide a table based on, right, some of the engineers experience of what is an acceptable range that they can, right, that if you see this value, it's accepted. Okay, so that's an example of an engineering rule that we have put in place. Okay, so this is, so this was a part of the demonstration that we did to the government agency a few months back, where we showed, right, the export plugins that we created. So this was one that we did for Revit. So for Revit, what is needed on the part of the user, of course, he needs to put in some of the information. We've actually created a plugin that will copy his information from the analysis and design and automatically populate the structural beam information. So this is to cut down on the time that he needs. So once it's done, then it's very basically a click of a button, export the information. And what you're seeing over here, this is the XMI schema. So it follows actually a JSON schema. And from the JSON schema, we can actually extract out the information that is required of the model. Okay, this is the proof of concept demonstration of our system. This was a very early stage POC that we did. We have one that looks a lot better now. So in this particular POC, this is still cloud-based. Allows us to, input data, create projects, and from there we can actually view the results in real time of the project. How many rules have been checked? Which are the rules that failed, and so on and so forth. We can then also zoom in on the trouble elements, on the problematic elements, to identify, okay, what needs to be done and where these elements are located, so that the engineers can do the appropriate actions. And finally, once he's done that, we can also generate a PDF that creates a report summary of what has been checked. Yep, so this is the report summary that was created. yeah, so basically that comes to the end of this part. Yeah, so the Connect X is going to go live in a few days. So 18th of December, it will be the soft launch. The focus of this soft launch, however, will still be on the architectural. We're still working on integrating our part with the Connect system. I'm looking at sometime June next year. And during that time, the soft launch will move towards the voluntary submission stage, which means that we will ask the engineers to submit out of their own accord. In 2025, we are looking at mandatory submission, which means the whole industry will start to submit all their designs in 2025. Very ambitious project, very ambitious goals. I hope we can do it. Yeah. Okay, and that comes to the end of my presentation on this.
Very nice. Very nice. I didn't expect that you're gonna present more than 1 hour. So
did I take more than 1 hour? I'm sorry.
1 hour presentation.
Oh no, I'm so sorry.
It's really inspiring, and then he brought a lot of information to this field of digital transformation or custom code, and then he explained the overall plan to the project in Singapore, and then also he didn't miss the technical part of this implementation. It's very helpful. You know, I think I found the really right person in this field. I'm very lucky. Do we have any questions for his presentations? Also from Kip. Yeah. No, so if you have probably any question, you can ask in Korean, and I can translate.
So I've heard that the IFC file has a lot of so big size, and isn't it hard for some industry companies to handle those big size files?
Yes. So actually, that's a very good point. One of the issues that Connect X is trying to address now, in terms of scalability, is this. So okay, so one perspective from the companies, right? From the companies, generating the files is not the issue. I mean, you're just generating the files. Whether you can open the files to check the files is another issue altogether, right? But for submissions, important part is to generate the file. Generating is okay, right? So now the problem is if you have a big file, right? So firstly, that's the reason why we Connect X, we have capped the submission to 800 megabytes per file, because anything that goes beyond 800 megabytes, it's very difficult to open the file and visualize. So that's the reason we're doing that. At the back end, I know that there's a lot of investment has been made on the Singapore government side to make sure that we can enable the government agencies to be able to open the files. So even though 800 megabytes, if you submit slightly bigger, it's still okay. It still can open it.
What's going to be the level of details with the 800 megabytes?
Okay, so level of detail depends. It's a very dependent question. I would say it's a design. It's one of the design thinking from our side is that we do not regulate the level of details.
Actually, in my group, I try to have the position of the level of detail as LODs as 300. Yeah, structural memory scheme.
So the difficulty with that, I think the difficulties with LODs is that it's very difficult to have a complete
target point, yeah?
Yeah, I mean, when you tell someone LOD, I want my PAL at LOD 300, right? It's actually quite difficult for someone else who does not know, right? What is LOD 300? So normally we will try to have a beam execution plan, right? That will spell out, oh, this is LOD 300. You need to have this information. You need the length. You need the reinforcements. You need the this. Now with that kind of documentation, yeah, you can, right? But if as you know, what we found out is that for one single project, it's okay to have that. But if you're trying to regulate this at a national level, it's very hard to tell people your PAL, your definition of LOD 300 must follow this, right? And then someone else's LOD 300 also follows this. So in terms of regulation, it's a bit tricky to have a definition of that across. So what Singapore government has done instead is to implement this as guidelines. That means we tell you what is the purpose, what is the goal that you need to do this for, and you model to reach that goal. Yeah. So we change the regulatory part a little bit. So instead of being prescriptive in telling you, okay, you need to have this, we now do it as a kind of like a performance goal. This is what you need. Give me the information so that I can do this.
Actually, here also you briefly introduced the data exchange schemes called XMI.
Yeah.
From the structural analysis code to the BIM. Actually, that's what I'm thinking of now. And then because once I prepare the digital version of the construction code, so anyway, I have to check the result from the structural analysis and design code.
Yeah.
And then can you explain about the concept of your XMI data structure?
Okay, so I would say that the XMI
is it open now? Is it open?
Yeah, it's open. It's open.
It's open.
Yeah, the website is there. You can
maybe I can refer to data structure.
Yeah. So I mean, I will also say this: the XMI that we have put up, this version that we have put up is still the early version that we were using. We have had some changes, some improvements to how we want the data to be captured. So, but I think my researcher hasn't updated the website with the newest.
Maybe I can provide my own viewpoint regarding the XMI data structure.
Sure, that would be good.
Which one of the points I have difficulty regarding, for in the case of your background is also structural.
Yeah.
So let's have an example of pre-stressed concrete girder. In the case of pre-stressed concrete girder, actually for the design stage you can play with the bending moment steps. Okay, but when we check, to finish the design, we have to check the stress value. But then how do you calculate the stress? We can draw the information of stress from the bending moment, but in these times we can take advantage of advanced finite element code where we can directly obtain the stress value. Yeah?
Yes.
So in the case of how we deal with all the different divergent data sources.
So that's the reason why we have not touched pre-stress. So
okay.
Pre-stress is pre-stress, post-tension. There are specific detailing information that.
And also shell structures.
Yeah. At this point in time, we have focused mainly on our public housing. So our public housing, we normally do not use the pre-stress and post-tension.
So buildings. Huh?
Yeah. So it's really buildings. Okay. That's why when I saw your slides that you were trying to do this for bridges. Yeah. It's very good, but it's an open question.
I have a lot ahead.
Yeah.
So funding agency is really nervous regarding the speed of research.
So the thing about bridges and roads, for example, for that matter, if you are looking at IFC as one of your design components, the good news is IFC 4.3, and I'm not sure how long your project is going to last. IFC 5 will be coming out soon, I think.
Actually, my project is for 4 years.
4 years.
This is the first year, and then actually I invited one of my colleagues for today's seminar because he is working on the extension of the IFC, similar to yours.
Yes.
We call IFC KR.
Okay.
I cheated a bit.
So the nice thing about the new IFC 4.3 and above, they have a new thing called IFC alignment. So the IFC alignment will allow you to model roads and bridges. Yeah, because that's the part that is missing in IFC now. Before IFC 4.3, it's all for buildings. Right? Everything is assumed to be flat and straight.
I see.
But with the alignment, then now we can do biaxial curves and things which are more common in roads and bridges and highways.
I see. Do you have any other questions?
Can you explain how can you write the rule? In our research, we make the manually code. So my question is, how can you write your rule, code rule?
So okay, so the coding of the rule, unfortunately, we have not come to the point where no code and generative AI to develop codes. That's something that we are looking at, but not so soon. I think where the code part is concerned, when we develop the codes, this is referencing back to the paper and in the other set of slides where I was talking about the conceptual graph. One of the useful things about the conceptual graph that would help coding. I mean, you can't run away from writing the code, right? What we can do with the conceptual graph is we can identify snippets of code that can be reused for different things. So for example, if you define, I need to find what's the invert level, right, of a drain. The invert level of a drain could potentially be the same as the invert level of a sewer, right? How you define that invert level. So when you develop the conceptual graph, right, for a code, for a clause that requires you to know the invert level, we can actually reuse that piece of the conceptual graph in another clause or in another conceptual graph. So what this means for you as a programmer is that set of code that you have done to identify the invert level, this identifies for you that you can actually reuse that.
Actually, so I'm really curious if I talked a lot during my last visit, because the conceptual graph regarding the construction code part is very similar to my rule set actually, and then I wonder if I cheated your idea. Actually, no, my plan is this. Actually, if I read the construction code, so many of them are not logical. Their brain structure is different.
Yes.
It depends on person by person. That's why in my research, I argue that we have to build a so-called rule set. Rule set consists of three parts. One is the first one is the metadata, the text part, and who wrote the code. And the second part is your conceptual data, like a flowchart. I'm calling it flowchart now.
Yeah.
And then the third part is the executable part of the code. And then with these three processes, and then I build one rule set, one rule unit. And then the combination of different rule units for different purposes, I call the rule set.
Yeah, actually, what you are doing is one of the So CornetX, when CornetX was developed, there's a company that actually developed the CornetX engine many years ago. That company is still involved today, developing parts of CornetX, and I know I know the vice president of innovation. His PhD is also in code checking. What you just described in terms of that actually is when they actually try to do something similar to what you've done. I think yours is a bit more complete than his, right? But I think the idea sounds similar. Every code that he develops, he has a document, and this document needs to be signed off by different people. And inside this document, he has the same thing as what you have. He has the metadata. He has who wrote this rule.
It's a bingo. So we are going to right way.
Yeah. So who wrote this rule? Which rule this is from? Which is the governing agency? Are there any other agencies that also interface with this rule? He tries to identify all these. Then he has the rule description where he writes out. So of course, he has the clause, and after he will explain out the rules. So what happens you're right. So what happens when people do these rules is that the domain experts actually have a lot of knowledge. The knowledge is not explicit. That means that they do not tell people outright.
Exactly.
So, but at the back of their mind, if you were to ask them, how do you measure this? Is this really what you are thinking about? They will actually be able to tell you in more detail.
Usually domain engineers are very weak in writing.
Yes. So so when he develops this document, he will actually sit down with the engineer or sit down with the architect, and he will start to ask and prod and probe. And then he will document all these things down inside his description. Then from this description, he then develops the conceptual graph. So the conceptual graph is actually his PhD work. Yeah, so that's why I worked with him. He's one of my co-authors. Yeah.
이거는 우리 루셋 얘기하는 거예요. 지금 이제 싱가포르에서도 지금 이제 그 니드를 정확하게 지금 파악하고 있고, 우리도 지금 방향을 제대로 잡고, 앞으로 이제 비전 센터에서도 룰을 새로 개발하고 관리할 때는 그 지금 우리가 설정해놓은 그 룰 유닛의 형태로 먼저 개념적으로 먼저 시작해요. 이걸로 플로 차트 형태로 이렇게 나오고, 그 다음에 메타데이터를 이제 그 플로 차트를 글로 쓰는 작업을 이렇게 해야 돼요. 안 그러면은 너무 복잡해요. 그러니까 심지어 이제 그 룰을 보더라도 이게 무슨 뜻인지 판독이 안 되는 룰들이 너무 많거든요. Yeah, it's a really good point. Do we have any other questions? From my funding agency? No? Okay, it's too late. And thank you very much for his good presentation.
Sorry, I took so long. I didn't realize.
Let's go for dinner. But by the way, is there any guy who cannot? We go to 만복시장, right?
그 바뀌어가지고
어디?
그 안목시장이 다 잡아가지고 돼야지가 돼야지야.
돼야지.
오징어가 나요.
그래, 같이. Do you eat pork? It's okay. Yeah, you're predator. Okay, let's go.